Alright, so we talked about breaking fractions apart, but we haven't talked about how to do it. So the partial fraction setup is what I want to go through here. So to use this partial fraction method I'm going to give you, it requires you to have proper fraction. Okay, so what that means is the degree of the numerator must be less than the degree of the denominator. So you cannot have something that looks like an x cubed over an x cubed. Bad. Okay. You also cannot have an x cubed over an x squared. So proper means that you would have something like an x cubed over an x to the fourth. Or an x over x cubed or something like that. So I'm just using cubes and squares here for whatever reason, but the numerator must have a smaller power than the denominator. That's what proper fraction means. If you don't have a proper fraction, you can use polynomial division to make that happen. And I'm sure I'll go through an example where that is needed. Okay, but keep in mind, you've got to have a proper fraction for this to work. So there's really two cases, but what you're going to start off doing is making sure your denominator is completely factored. So you're going to factor the denominator. So I've got some examples here, and just to kind of look at them, I'm not going to worry about what the numerator is. We're going to assume it's a proper fraction. But this denominator is factored into x times x plus 3 times x plus 5. Okay. So when you have your denominator factored, as long as every factor is completely different, there's no repetition, what you're going to do is you're going to create a fraction with a denominator for every single factor. So that means the x in the denominator will be the denominator of its own fraction. The x plus 3 will be the denominator of its own fraction. And the x plus 5 will be the denominator of its own fraction. Okay, so this had 3 factors in the denominator. So we're going to have 3 different fractions. Now when you set these up, you need a numerator as well. The numerator must be 1 degree less than the bottom. Okay, so over the x, which is to the first, we'll have just a constant. Okay, that's degree 0, just a constant. Over the x plus 3, we'll have just a constant. Over the x plus 5, we'll have just a constant. So we'll call those different constants a, b, and c. So it'll break into a over x plus b over x plus 3 plus c over x plus 5. Okay. Now, let's skip to the third example I have here. This is a fraction, and the denominator is factored into 4x minus 3 and 5x cubed plus 6. Okay. So looking at that, we have 2 distinct factors that won't break down anymore, so we're going to make 2 completely separate fractions. One's going to have a denominator of 4x minus 3 for that factor. The other one's going to have a denominator of 5x cubed plus 6 for that factor. Okay. Now we need to go back and we need to take care of the numerators. So 4x, that's to the first, so we only need a constant for the numerator. So we'll just have a. For the second fraction, 5x plus 3, that's a cube. That's degree 3. Our numerator must be of degree 2. So we'll need an x squared. And it needs a coefficient, so it'll be a bx squared. But we don't know if there's anything after it, so we're going to set it up generically to contain any second degree polynomial. So that numerator will be bx squared plus cx plus d. Okay, so any denominator you set up, you need the numerator to be 1 degree less. Okay, and you need to account for any term that could be there. Okay, because we don't know what a, b, c, or d are yet. We haven't got that far. The one exception to this is if your denominator has a repeated factor. Okay, this is handled a little bit different. Okay, so if all your denominators are different and only show up once, use the above method. If anything is a factor more than once, you're going to tweak it just a little bit. So this example, the denominator is x squared times 3x plus 5. So if something repeats, you're going to use every power of that repetition. So with the x squared, the x is the true factor. Okay? So you're going to use an x to the first, but since it shows up twice, you're also going to have an x squared. And that allows for the fact that you could have different values up top. Okay? The 3x plus 5 is going to get its own fraction just like above. So we need to focus on the true factor, which in this case is just x to the first. So we're going to make the numerator 1 degree less, which will just be a, the constant. And every factor that or every fraction that we build after that, we'll use the same type of numerator. So even though we're using an x squared, the true factor is x, so we'll still use a constant there, just b. And over the 3x plus 5, we're using c from above. Okay? Now, moving away from that, the next example, the last one here that we're talking about in theory, is the denominator 2x squared minus 5 cubed. Okay, quantity cubed. So we need 2x squared minus 5 3 different times. We need it in the singular, we need it in the square, and we need it in the cube. Okay, so every time a factor is repeated, we're going to use every degree of that repetition. The true factor is 2x squared minus 5. Okay, but it happens in different stages, so we'll use each one of those stages. Now with the true factor, 2x squared minus 5, the numerator will need to be 1 degree less than that square, so ax plus b. And we're going to use that same setup, but with different call letters for the other ones. So even though the next one is squared, we're still going to use cx plus d and ex plus f. Okay? So in all these cases, we use a numerator that's compatible with the definition for the single true factor. Okay, let's try and do an example here and see how it goes. I'm going to need to take this to another page. So let's just steal it. Let's come over somewhere and get us some room. Sorry. All right, so here's the fraction we're going to work with as our first example. It is 5x minus 7 in the numerator. Denominator is x squared minus 3x plus 2. So the first thing we need to do is see if it is proper. So the degree of the denominator is 2, and the degree of the numerator would be 1. So we're okay there. And now we need to factor the denominator as much as possible. X squared minus 3x plus 2, that factors into x minus 1 times x plus 2. So the numerator stays the same, 5x minus 7. So let's write this up. 5x minus 7 over factors x minus 1 times x. That should be minus 2. I don't know why I wrote plus 2 there. I'm sorry. So the two factors here are x minus 1 and x minus 2. And both of those are degree 1, so the denominators will just be the numerators will just be a constant. So we'll have a over x minus 1 and b over x minus 2. And those are interchangeable depending how you set it up. So that's the setup we just went through. Now we got to look at how you solve this. So what we're going to do is set up like a rational equation and try and get rid of these denominators. So we need to multiply through by the common denominator, which would be x minus 1 times x minus 2. So that's going to hit every single fraction we have. Okay, all three. Okay, and then we'll come back and cancel out any terms we can, which if we do it correctly means there should be no denominators left. Okay. And as we clean that up, we should have a linear equation or maybe even a polynomial equation, but it'll be 5x minus 7 on the left On the right, we'll have a times x minus 2, so we'll have ax minus 2a. And then we'll have b times x minus 1, so that'll be plus bx minus b. So now what we're going to do is we're going to compare degrees on the left and the right. So we'll color code this, kind of help you see it. So the largest degree we have at all is just the first degree, which is an x. So if we look at these, what I usually like to do is say this is my x term. And what do I have? On the left I have 5 of those, and on the right I have a plus b of them. Okay? And then I need to move to my constant. And let's color code that with something else. We use green. So on the left I have negative 7. On the right I have negative 2a minus b. So let's write that down. Negative 7 equals negative 2a minus b. So what this gives us in this particular case, and it could be different in other cases, is 2 equations, 2 unknowns. So a system of equations. I'm going to solve this with elimination. I'm actually going to add the 2 together. So I'm going to stack them on top of each other. 5 equals a plus b over negative 7 minus 2a minus b. And I don't need to do anything to kind of fix this up. And the reason I'm picking elimination is I notice if I add them together, the b and the negative b cancel out. So that will give me negative 2 equals negative a. So a is 2. And if I come back, if a is 2, I can go back to 5 equals a plus b. That means 5 equals 2 plus b. So b equals 3. So I can go back to my partial fraction setup and say that what I've learned is that this partial fraction I started with, which I broke down into 5x minus 7 over x minus 1 times x minus 2 is equal to a, which is 2, I'm coming up here, 2 over x minus 1, plus b, which is 3 over x minus 2. So there I've broken it apart. Let's take it one step further. Let's come back in here and say I want to integrate each side. Well, you can go back to the original up top and notice that if you try to use substitution on the 5x minus 7 over x squared minus 3x plus 2, it just doesn't work out. So I'm not able to use the u substitution there, but over here with the partial fractions, I can. Okay? And these partial fractions will integrate. The 2 over x minus 1 will be 2 times the natural log of x minus 1 plus, and the 3 over the x minus 2 will be 3 times the natural log of x minus 2. And don't forget your plus c. So this thing that we had in the beginning, we couldn't integrate the way it was. We went through the partial fraction technique, and we got something we could integrate. All right, so that's our goal. Got to get used to the partial fractions, got to get used to finding these coefficients, and then we'll be able to integrate. Thank you.